we've had, as many of you know, we've had enough ecstasy and pain and suffering around data and storage in particular, in the last year, that we felt it would be appropriate to take stock a little bit. And we asked ourselves, how do we do that best? And so we arrived at a three-piece process. Derek's going to go for 20 minutes over what do we offer what does the infrastructure actually have? What are the options? And then we have a panel of users who will tell us what are they doing with those options that Derek has just talked about. And then we'll have 20 minutes of this. That will take another 20 minutes. And then the last 20 minutes, we'll have a free-for-all of everybody else and to join in and discuss. And we'll see where that goes. Sounds good? Derek's first.
All right, thank you, Frank. So I'll talk about the storage options on the NRP, and of course, any chance I get to show off some of the maps and dashboards that I make for the NRP, I definitely will. And so you'll see this map hopefully several times in the next 2 days. So we have a range of storage options available on the NRP, and I'll go over them individually, their advantages and disadvantages of each. And each one has a little bit of a trade-off. But I want to stress the importance of picking the right storage option for you. Picking the right one can dramatically affect the efficiency and how long your workflow runs. But there's kind of two dimensions to this: the storage type that you choose and the region. And I'll show you some metrics that I've created to show the difference, that not only choosing the right technology, but choosing the right region, since we are so geographically distributed, dramatically matters on the performance of your workflow. But as with anything, it's always a trade-off. And I created this. I'm a huge fan of spectrums and trade-offs and kind of understanding where you are. And using a very unscientific, my opinion, I created a spectrum of storage technologies and ease of use. So as you go further to the right, it's easier to use. CephFS is very easy to use on the NRP. Ceph RBD, a little bit more difficult to use, has a few more restrictions, still easy. And then you have a GAP, and S3 and OSDF are on the left. They're less easy to use, and I'll talk about why that is here in a moment. But as you go to the right, you get easier to use, but at the same time, the scalability goes down. So as you go to the left, you're able to process more data, you're able to transfer more data more quickly, you can have larger data sets as you go to the left. And so it's a trade-off, easier to use versus scalability of these solutions. And so I want to go over the technologies real quick. So the first one is CephFS. This one is many people's favorites. It's easy to use and partition. You can share data within a namespace between multiple pods. So it can be useful if you're sharing data between a lot of different ones. And it appears like a global file system for the users. So it's a very familiar feel. There are some disadvantages. The complexity in the implementation of CephFS means there's many more points of failure. For example, CephFS was out for a better part of a month last year due to one of these components actually failing quite dramatically before we were able to restore it. There's also a little gotchas with CephFS. Conflicting pods can cause odd issues with file locking. And then one of the disadvantages you'll see kind of commonly with this one and the next one, the Ceph RBD, is you have to stage the data there somehow. You have to get it to the cluster, and that's, for the most part, is left as an exercise. And then it has slower performance with lots of files, and I'll show you some actual hard data to show that. Now, Ceph block device. Again, it's easy to use and partition. It just mounts right to the pod. It's a simple implementation, especially compared to CephFS. It means a lot less failure points. For example, during that outage where CephFS was out, this technology, Ceph block devices, continued to work as if there was no issues. And so there are less failures. And there are some niceties. It has much better performance with lots of files. And you can also do things like you can copy the PVC, which in effect makes a copy on write copy of it. So I've helped classes that do this. The instructor creates a master PVC, then every student gets a copy of that PVC with input data, with image sets. In this particular case was image sets because they were doing some AI training. Some disadvantages: it can only be mounted, unlike CFFS, it can only be mounted on a single pod at a time. There's no sharing of data between pods. And then the same thing as the previous one. You have to stage data somehow. Another storage technology we have is S3. So it's available from all pods, and it's available from your laptop. And this is actually a screenshot of me accessing the S3 interface on Nautilus using this technology. This is CyberDuck on my Mac, but there's many different tools, graphical user interfaces to access this type of data. And again, it's simple implementation, leaves less failure points. The disadvantages is there's no mounting on the file system for your pods. So the only way to access data on your pods, or access data from your pods, is to use very explicit tools to get or put data into the S3 storage. And there are some ACLs that you can play with, but in general, either you make the data public, and public read-only is an option, or you have to handle credentials within the pods. You have to handle access keys and things like that. And so that's a downside. You don't have to worry about access keys in the Ceph world, in the Ceph RBD or the CephFS. That's all handled for you. But in the S3 world, you do have to handle that. The OSDF, again, very similar to the S3. It's available from all pods. It's available from your laptop with the right tools. Some of the advantages: it has distributed caches throughout the world. And so you're not so locked in on these regional issues that I'm going to demonstrate here in a second with actual numbers. You don't have to worry about those quite so much because these caches are regionally distributed. And frequent and repeat access can see speedups over our current S3 access. Same disadvantages as the S3. You cannot mount this on a file system, so you have to do very explicit puts and gets within your pods in order to get the data. And same thing, either you make the data public or you have to deal with credentials. And we're constantly making the credential handling easier, but it is still a step you have to do. And then one more technology, a storage option that is not a persistent storage option, but can be useful if you need really fast access just for a single pod, is ephemeral storage. The main downside that I really want to emphasize is ephemeral storage goes away when your job goes away. And so anything you want to keep, you have to upload to one of the other options that I highlighted earlier. But the nice thing about ephemeral is it's very, very fast. It's almost always on NVMe, on the node that your job is actually running on, so it's very, very fast. As you ask for the ephemeral storage, the larger amount you ask, it is a trade-off. The more you ask for, the less nodes that are capable of handling that type of request. And so you have to kind of size your ephemeral storage request accurately such that you don't over-ask and then you lose out on potential resources that you could have ran on. So there is a little bit of a trade-off. So put some numbers behind. You have to pick the right region and the right technology. So let's say you wanted to install PyTorch in your PVC. And I ran these tests. So if you install PyTorch on CephFS, it would take about 5 minutes if you were in the western region and 25 minutes in the central region where I live. If you use Ceph RBD, it take about 25 seconds to do the exact same thing in the western region and 33 seconds in the central region. And the reason is that CephFS, because when you're installing these Python packages, it's a lot of small files that you're dealing with. And CephFS has a lot of metadata operations that have to go external. All of them have to reach external servers to do all these metadata operations. There's no metadata operations in Ceph RBD that have to go external. It's all in the storage itself. And so because of this optimization for small files, Ceph RBD is the better choice for this case. But not only technology matters, regions matter. And so what I did is I tested reading and writing a simple 50 gigabyte file across the region, and then I normalized it to the Western region. And so what you'll see is that to write a 50 gigabyte file in the central region it's 1.3 times how long it takes to write in the Western. And then it's about 2 times to write in Eastern. Now, I want to highlight that we have technology turned on the NRP for write caching. And so some of that write latency is hidden from you. It'll cache the write on the node your job is running before it slowly siphons it off to the actual storage. So some of this latency is hidden from you, but you do definitely see it in the reading. If I read the 50 gigabyte file, it takes 5 times slower to read it in the central region and 9 times slower to read it in the Eastern region. And so not only does technology matter, but also the region that you're running on also matters. And so this is a bit of a trade-off. You have to trade off where are you going to store your data and where are you going to run your compute. Either way, you have to make a trade-off because you're excluding either compute resources or storage resources. If you choose the Western Ceph and you only run on the Western, then you're excluding a tremendous amount of GPUs that are housed in the central region and in the Eastern region. And the same goes for if you store everything in central and want to run in central, you're excluding a lot of GPU resources that are on either ends of the coast. And so it's a trade-off that you have to make. But unfortunately, there is no great idea. So some of the technologies like the OSDF kind of minimize that regional choice effect, but you still have it to a certain degree. I want to leave you with some closing thoughts. Choosing the right storage option for your workflow requires knowledge of your I/O patterns. Now, I've talked a lot about these regions, the technologies, and which ones you should choose. But generally, a good rule of thumb, if you don't know which to use, a bad default is the Ceph RBD. It's probably not going to be optimal for your workflow, but it's also at the same time not going to be a terrible choice. It's not going to harm your workflow tremendously. Please keep in mind the trade-off between the storage regions and the compute regions. Try not to leave too much compute, available compute. If you're having a hard time getting your pod started or whatever, it could be that you're restricting yourself to more of the storage. And in that case, it might make sense, even if your workflow runs a little bit slower, to use available computing resources in other regions. And the last one I want to leave you with is the OSDF, which is designed to minimize these impacts of regional storages. It's constantly evolving and constantly getting better. Both the handling of the storage, the tools that are used, and then also credential handling is constantly getting better and improving, such that the barrier of entry into the OSDF is getting lower and lower, I would say monthly. And so please continue to pay attention to that. Okay, that's my presentation. Thank you. Next, I'll have David come up.
Do you want to ask if anybody wants to ask?
Do you have any questions before?
So I wanted to see. So are you recommending we go to OSDF as far as speed of and latency of the I/O and all of those options go?
What was the first couple words? Sorry.
So are you recommending we use OSDF to get better read-write latencies beyond optimizing region and compute choices and so on and so forth?
Does the OSDF give you better read and write latencies?
Yeah.
Potentially, especially for shared data. Yes, it definitely can. For single access data, you're probably not going to see a whole lot of improvement depending on where the origin of that data actually lives. But
so it's more for shared access. Is that more precisely?
More like frequent, kind of like a CDN, more like frequent access or repeated access would probably be the right term.
Got it. Thanks.
Any other questions? Good. Then
Okay, Dave. Thank you.
thank you. So I'm going to
talk about a use case we're using of NRP to train, test, and use large satellite foundation models. We've all seen the exponential growth in large language models. A similar trajectory is starting to happen, taking global sets of satellite imagery to create similar types of foundation models that then can be used for downstream tasks. I'm with USRA, so I'm going to give a little introduction of our organization. Some of you may not know it, and then get into some of the details of the use case. And we've been a partner with NRP, PRP since 2021. One of our PhD scientists got their PhD at UC Irvine. He did his PhD using machine learning with NRP. He came and joined us, told us about it. I was like, okay, I got to join, bought some NVIDIA GPUs. And we've had community college kids, Berkeley students from all over who train on this infrastructure and then join our workforce and join other workforces.
Can you speak closer to the mic?
Oh, sorry. So we're very appreciative for this partnership with NRP, with Larry and Tom as our initial introduction, now with Frank. A little piece of our history which surprises people a little bit. USRA as an organization was founded the year man first put foot on the moon to make collaborations among academia, industry, and government, primarily with NASA, but around space, science and technology, research, development, education. But in 1983, Ronald Reagan was president. Every year, the President of the United States sends an annual space and aeronautics report of the President to the US Congress. In the report that Ronald Reagan sent to Congress in 1983, it said industry is making rapid advances in artificial intelligence, supercomputing, and human-computer interaction. This is important for aerospace. And as a result, was creating a new computer science initiative at NASA and also making a major commitment to establish the institute that I run, this Independent Research Institute for Advanced Computer Science at NASA Ames, operated by USRA. It's an amazing part of the history. You think AI in '83, wow, that's a long time ago, but only AI is just coming onto the scene now really in great fold. It is a transformative moment now, but we have made a tremendous amount of progress over the years. Just a few quick examples. In the '80s, we came up with an unsupervised machine learning approach that became the first AI to make a published astronomical discovery. It discovered a new class of infrared stars, was later recognized for making a seminal contribution in unsupervised machine learning. In the '90s, put AI onto a spacecraft, launched it in deep space, had it take over control of the spacecraft. They simulated failures, it detected those failures and recovered from those failures. In the 2000s, the Mars Spirit and Opportunity rovers, the plans, the work plans for those every single day was made using software that our team developed with NASA and academia. All of these things are with NASA academia collaborations, but with USRA scientists deeply involved. Also in the 2000s, 5 years before Siri, we had Clarissa up on the space station, had a conversation with an astronaut in space. More recently, we've got AI for aviation, commercial aviation, recommending reroutes to reduce fuel use and emissions. And airlines are taking those recommendations, going to air traffic control, getting approval, and actually rerouting commercial aviation with those. As I said before, we started a quantum AI lab. I won't talk about that, but we partnered with NRP, should be on here. I have a line there, it doesn't say it, but we partnered with NRP in, as I said, in 2021. And with this transformative moment, all of these AI achievements, there is a fundamental change going on. With generative AI, in my mind, it started with the Google Transformer architecture in 2017, and then the generative pre-trained transformer, GPT, that OpenAI came up with, and all the evolution that's been going on ever since. But so to adapt to that change, we formed this Generative AI Lab for Science and Engineering last year, a partnership with Boston Consulting Group, their software development arm, NASA, and then of course we're using NRP as part of this lab. The very first major task we've been taking on, and this is the use case that we're using a lot of NRP resources now for, is to train a foundation model for a satellite foundation model for multiple downstream use cases. So it's this thing where historically all of these AI models we developed were very task specific. They did one thing well. But now you can train a foundation model just on the satellite data itself. It finds the patterns in the data. We take decades of global satellite data that's hourly. It's a fair amount of data, and it takes a long time to train this model. and then you can use it for many downstream use cases. And so in our case, we're focusing right now on precipitation, tropical cyclones, and atmospheric rivers. We started kind of building the algorithms for this, and then starting building the workflows, and it's evolved over the course of the past few months. You can see it's taking a fair amount of GPU usage at the moment to train this model. It's a model that we're not sure how long it's going to actually take to finally be trained. Well, right now we're estimating about 15 days running around the clock 24/7. So happily with this model of NRP, we were underutilizing our NVIDIA GPUs when we joined, but now we're definitely taking advantage of the pool resources. So when it comes to data, and let me show you on the next slide, and then I'll come back to this one. So we pulled in the raw satellite data into Ceph-FS, about 77 terabytes. And then we converted, that's in CDF format. Then we convert that into ZAR files, get down, and we put it onto S3 down to about 15 terabytes of the data that we need for the training. So we were in West, then to address a few issues with access in the fall, we switched to East. And the key thing is then we have to get that data to the GPU nodes. So 15 terabytes of data, we then get it to the GPU nodes, and we create a cache there. So it converts into about 4 terabytes of tensor data in the cache in the GPU nodes. Once it's there, we're just reading from NVMe, that ephemeral storage we just heard about, which is very fast, but it's a lot of reads still. It can be extremely parallelized. So the more GPUs we have, the better. We're limited now because we have to get those tensors into the memory of the GPUs. And if we have 24 gigabytes of tensors in a GPU, it's not all in memory. We have to read. So we estimate about 83 million reads over the course of training this thing. It's a lot of reads, even though it's the fastest reading possible. And so we were using 32 GPUs, now we're using 48. We went to 810s just because they were more available, even though they're a little older on the NVIDIA side of things with less memory. But we found that was a way to kind of distribute the workload more. Again, we think it's about 15 days if we had 10 nodes. We're not really sure how long it's going to take to finally complete. When we went from, just a couple of notes, when we went from Ceph-FS to S3, we got about a 10x speed up, which was good. And now with that cache, also we are, for the first time, we're going to harvest that cache so we can, when we need to restart, we don't have to rebuild the cache, which takes a little less than a day to rebuild that cache. And then we have checkpoints. Every 3 hours, we're doing a checkpoint. So if there's any glitch in the infrastructure or our algorithms or anything, we can restart without going back to square zero, because it's a long run, and so that's a long time to run, especially when we work 40-hour weeks. This team here works 40 plus, but it's a long time. So a couple of desired capabilities, certainly higher GPU memory. If we could do this all in memory, like if we had 8 Grace hoppers, that would be ideal. The data transfer speed between the nodes. We're not sure, the limiting factor right now we think is the 83 million reads off that non-volatile memory. But data transfer speed between all nodes is something that we're interested in. Monthly stats on data use would be interesting just to track our use of NRP resources. I think those are the big ticket ones. Thank you. Questions? Or do you want to wait to the panel?
Let's do this.
Yeah.
Let's go through all 3 and then do all the questions at the end.
Okay.
Unless there's something specifically that you will clarify. Can you go to the mic, please?
You said you're expecting 15 days, but did you finish training the model or
No.
not yet? Not
No,
yet.
we're still, it's running right now.
Okay, I see. Okay.
Yeah.
All right, we should email you in 15 days.
We'll see. Yeah, hopefully it resolves in about 15. We'll see. Thank you.
Hi, my name is Bo. I'm a student of Professor Hao Su at UCSD. So I will present some use cases of NLP in our lab. So the directions of our lab has two main directions. One is computer vision, and the other is robotics. So they have different requirements for I/O and data storage. So for computer vision research, we mainly use CFFS and F3. So in terms of I/O, we need both reading and writing data sets required for model training. But usually we don't have simultaneous read from the same files from multiple containers. And we don't usually write to the same files from multiple containers as well. And for the writes, usually we could write to local disk and then transfer the files to CFFS or S3 if we want to share the data set with external collaborators. And in terms of scale, we usually launch hundreds of containers at the same time. And yeah, so that involves simultaneous reading or writing to the same storage, up to 200 containers, I think, in the past half a year. And the usual dataset size for our computer vision research is usually 10 to 100 terabytes, and that's usually for storing image and object 3D models. So our research has been leading to some publications in top-tier artificial intelligence conferences. So here are some results on open world 3D generation. Basically, we have models that can just take in a bunch of 2D images in the wild and generate 3D meshes in just minutes. And this has been adopted by some companies in the industry. So in terms of robotics research, we still majorly use CFFS and S3. And in terms of I/O, we actually need more reading than writing. And the reading is usually for loading data for supervised learning. And for reads, there could be multiple containers accessing the same files, though we try to minimize reading the exact same files to have more I/O bandwidth. And so usually high-speed reading is preferable to prevent I/O bottlenecks. So for robotics research, we found that if we can have I/O that's closer to 10 gigabytes per second, that could help us mitigate our bottleneck on I/O and transfer the bottleneck to GPU or CPU. Yeah, in terms of writes, we don't write to the same files for multiple containers, but we heavily write on the same storage. And it's usually for collecting synthetic data for robotic training in simulation. And usually we write to local disk or CFFS and then transfer the data to S3. And writing speed is not a major bottleneck from our experience. And in terms of scale, the data set size for robot learning is usually smaller, so it's roughly 1 to 10 terabytes, usually a mixture of images and then some other NumPy arrays. And usually we require simultaneous reading from the same storage in up to 100 containers. Yeah, that's roughly the usage in our lab. Yeah, thanks.
I'm going to break my own rule and ask a question.
Of course.
Anyway, if I understood this right, then you could, with no negative side effects to how you operate, switch from CFFS to CFRBT. Is that correct?
I actually think so, though for some reason, it seems that the students of our lab don't use CFRBT very often, but instead we use CFFS. Yes.
So there's basic CFFS for familiarity and convenience, but if you ran into trouble that things don't scale anymore on CFFS, you could just switch to CFRBT and you wouldn't make any difference.
I see. Yeah, that's a good suggestion. Thanks.
Okay. Does anybody else want to violate my rule with asking questions at the end? Okay, and the next.
I don't have slides, but we'll see if I can navigate the web to show off what I'd like to. So we'll see how this works for us. Yeah, you know, those are always scary, right? Okay, so I'm Kyle Krick. I'm a research software engineer at San Diego State University, and we've been using National Research Platform for about 2 years now. We started out with our instructional cluster. So along with San Bernardino, we were putting our toes in the instructional space on NRP and learning some lessons there. Oh, pause for emergency notifications. Okay, well, hopefully nothing too serious. If it is, come get me off stage. So my focus will be a little bit different. I am focused more from a research facilitation perspective. And should we... Oh, Amber Alert? Okay, well, hopefully they can solve that quickly. So basically what I do is I partner with our faculty, with our researchers, with our undergraduate, postdocs, etc., students, and advise them based on what workflow they have, what storage is the best option for what they're trying to do. And not to talk about a subject too much, but one of the biggest things that we've run into is large language models. Specifically, we have a lot of courses. This was surprising to us, but we're having a lot of courses that said, oh, cool, we have access to GPUs. Well, I've heard about these large language models, and I'd like to fine-tune them in course, in the middle of class. So you can imagine that these large language models, as the name implies, are large, so they require a lot of space. Then as you go to do fine-tuning, you end up taking up more of that space, right? The other thing is, a lot of these large language models have the same weights, the same files. So we're duplicating data. So we tried to use, let me see if I can scroll here. We're trying to use file storage, CFFS, but as that was pointed out, can be a bit slow. And some of the tools that are out there will actually say, hey, this is taking too long, I'm going to give up. So we're trying to solve that problem of data duplication, because it's literally the same bits copied over. You know, if you have a class of 50 students and you download Llama 70 billion, you've got 50 copies of Llama 70 billion out there taking up space. So that's just one example of what we try to do to advise people on throughput. I've got this matrix here that looks decently large up there on the screen. So essentially we're trying to present in a table format what Derek was already presenting, right? So when do you use which type of storage, right? And that's going to depend. So ephemeral storage, it is very high performant, but the issue is getting the data there to start with. So we're trying to advise the use of S3 because that's the most scalable one. And S3 is the only storage option that is accessible outside of its namespace. And for that reason, it allows you to scale a lot better. So on our campus, a lot of our users are familiar with Jupyter Hub. And so we run one instructional Jupyter Hub, one research Jupyter Hub. So what they'll do is they'll use Jupyter Hub because that's the front door. It's the easiest way to get started. And then at some point, they need to start scaling up. And if they only have stuff in their block storage, which is their default for Jupyter Hub home directories, well, now they need to move things to be able to scale inside of a namespace that's external to that Jupyter Hub namespace. So we're trying to push S3, which, as we talked about, does take a little bit of a, there's a bit more of a learning curve with that, but the scalability that it offers is great. So something else that we're doing is trying to go through and explain when you might use what type of storage, right? And what that pattern looks like. So block storage, right? So if you're just using Jupyter Hub, maybe you'll just do block storage in your home directory space. At some point, it might make sense to start using S3 into block storage into a namespace. So that way you could start parallelizing your pods that are processing on the same data. And then you can copy that to block storage for quicker access and more natural access, because not everyone is familiar with REST APIs and all the various tools that you can use to interface with S3. They're more familiar with just regular file storage, just, you know, Linux, open up this path and load it into RAM. So that's what I'm focused on, is trying to help people out there apply these technologies and these data storage options to best meet their need. So that's from my perspective.
Hi, everyone. I'm Dinesh Paradia, professor at UCSD department. I've sort of last year presented a lot of work on radars and how we have used radars to do perceptions and autonomy and so on and so forth, right? So broadly, my group works on everything related to wireless, right? So we have a lot of perception, sensing related tasks, right? And then we develop a lot of machine learning algorithms for that, right? So broadly, there are two use cases we have. One is generation of the data. So we run a lot of Unity-like ray tracing models and simulations to generate accurate RF emulation of what environment would look like. So that's one use case. And then we also have a lot of use cases where we sort of have just generally, once you have to generate even this data, we have to generate or create 200 plus containers, right? And they just sort of start writing to one same storage, right? So that becomes a one write problem we have, right? To writing to central location. And then once these containers are done, they sort of shut down and whatever, the data is stored, right? The next stage, once that data is generated, is sort of to have multiple sort of nodes parallelly using the same data and accessing that same data to train LLMs and different types of models for that matter. So these are like, let's say, two primary use cases we have, right? Generation and let's say then using of those data, right? And I think there are some auxiliary use cases we have realized in recent times is we have done. We actually have our own chat studio deployed in it's funny, it's interestingly deployed. Just the front end of the chat studio is deployed in the NRP because it's available all the time. At the back end, whenever we are to call inference for our own models or maybe slightly more complex models, we have some specialized GPUs for our lab. So that online service either can call OpenAI models and other things if you want in a single platform, but it can also call our self-hosted models, right? So it sort of becomes just a web service provider at some level. But that also works well for us because that gives us guaranteed performances for some of the access of our own self-hosted models and then the cloud-hosted models by the large companies out there, right? So that's another interesting use case evolving, and more we are moving a lot of people into using desktops itself in the cloud, right? I think Amazon also offers this service, right? But I think we try to balance both sides. Sometimes we use NRP as well for some of these MATLAB desktops, which are pre-installed with MATLAB. And then you can just immediately get on there and get people to train. And this also we use for our classrooms a little bit, right? So those are like broad use cases, right? I think standard issues, I can go about some of the issues we have faced, right? And I think, so one concrete problem is, I guess, always sort of lack of different use cases, right? On one use cases, we are write heavy, right? Where we are trying to write to single storage, right? Or single PVC volume at some level from different 200 containers and trying to, let's say, take 200 scenes and evaluate those 200 scenes and generate data for all of those, right? So that I think is a write-heavy task, right? Okay. The key problem really we face in the read-heavy task when we are trying to train a same model across multiple containers, right? I think that is a real pain point for us, right? I think the Ceph RDB could be another thing to explore for us, right? So we are primarily using Ceph and S3 in combination of these things, right? Ceph FS and S3. On the other side of archival data is another big problem, right? So we have had generated lots of data sets and often we don't find any space on NRP for archival data. So this is one problem I don't think was sort of addressed by other speakers. I think other speakers covered largely the problems we are also facing. So I don't want to reiterate on those. But the archival data could be, and I do apologize, maybe this is my lack of information here on the archival data, but that is the other problem. And I will pause at that and give it back to Frank. Yes.
So can I ask for the writing?
Yes.
Should I go to this microphone?
No, I'm okay. I can hear you, but I can repeat your question as well. Yeah. For writing, yeah.
So for your writing,
Yes.
Could you write locally and then end with a put? Or do you have to write from multiple containers into the same file?
We can do put. I think that was one interesting thing when he presented OSDF, right? I think that seemed like an interesting variation if that helps us with. So we can do a local write and then move it by using get or put.
So you could for all of your writing workflows, you could just replace the Ceph with S3.
Yes.
And that wouldn't make any difference.
Yes, it wouldn't.
Okay.
Yeah.
I think that would definitely be
significantly helpful. I can imagine.
I want to make clear, we picked these people in part because they're some of the heaviest users and they were
Exactly.
willing to stand up and be screamed at and engage with us. But in part also because if we can, and if we can move some significant amount of activity away from CFFS, CFFS will survive longer. And
Correct.
it will make everybody else's life easier.
Correct.
And have to be, if we could get the large use cases wherever they're possible, move from CFFS to S3, then when you look at Derek's slider,
Right.
from easy to easy to use to less easy to use,
Right.
then the easy to use CFFS stays for those who are smaller in their needs, and the people who are larger in their needs and need the scalability, if
Right.
we can get them to move to more S3 use, everybody wins.
Got it. That is a great idea. I think we can definitely implement. Actually, maybe I have a suggestion for this on this other end, right? Okay. What happens is, I think today's session was amazing for me, right? I learned about so many other ways from your questions and some of the other presenter, right? Is there I'm sure there is one, right? I have to say that I may not have used it, right? Okay. That there is an office hour where student can just go discuss their project use case, and then you can also give suggestions, right? Instead of just, I think often reading documentation, what students would do is that, okay, my former student did this, right? I just follow that, right? I don't have to invent the wheel again, right? So they just kind of follow the same footstep. But if there is perhaps, let's say, even there is a chat GPT model for NRP, that is also perfect, right? We can have that, right? And then we can ask the questions directly. Hey, I'm trying to do this project where, so for our case, what you just said is perfectly fine, because what we try to do is that we simulate 200 towns, for example, right? And we try to place a base station. We try to understand the coverage studies. We try to do some of these things where we are trying to understand propagation and how it would work, right? All of this is parallelly. Nobody has to interact with the other town, right? Maybe very rarely they have to interact, right? So we can all store locally and then do the put and the get stuff, right? From OSDF. That could be an interesting variation if it sort of solves and minimizes. The problem is that the compute is also blocked until the data is not stored, right? So that also creates worse for the utilization as far as the utilization goes. So these are, probably there is already an office hour for students to go.
And the office hour question is actually an interesting one. Do you want to comment on that? Up there, I see hands up. So we don't have an office hour. Why don't you go to the thing, because we're recording? The microphone.
Yeah, so we don't have an office hour as of now, but starting from this year, we have been planning since last year that we want to have office hour very frequently, at least once a month. And also we have some presentations. Usually we sometimes give presentations to university groups about NRP and how you can use it, or what are the resources. So we could also do that for your group if you want. So that's one thing. And then office hours, yes, we'll probably promote the office hours more.
Sounds perfect.
Yeah.
And one more suggestion, right? We can just train a RAG model, and that way just your documentation is already there. Just nobody bothers to read it often enough, right? That is also I think.
Yeah, so
it's just a matter of
Mohammed is actually working on it.
generational
We are also started working on LLMs and doing RAG with our documentation and chats. It's still not done yet, but yeah, eventually, down the line in few months you'll see that.
So I am tired of having to deal with my talks with spreadsheets. So one of my goals for the next year is that I myself have access to all the information that I normally do in order to make my talks,
Right.
in a form of some kind of LLM, and I call it the director's LLM. And because the kind of questions I have are not how to use something, but what's going on, right? And so there's probably going to be more coming like that.
Sure, sounds perfect.
James.
I was just going to suggest, I mean, this is maybe for the folks that are operating, but these stories, these office hour type efforts, they're happening via Matrix at times. And I think there's some eye-opening successes of shifting people and a repeatable workflow. I would love to see maybe a blog post, because those are the types of things that when you see it in practice and see that it's something that can be done. Because there's been a few cases back in a prior role where it was an aha moment and it was just word of mouth. And so I don't know if turning some of that word of mouth into something more than just a document, but something that kind of steps through the impact that had, that would be real valuable.
Perfect. Yeah.
Any other questions? Can we bring up David's slides again? Because I have some questions for David.
I have a comment and a suggestion for the speaker from CSU. What you presented concerning storage, your goal of informing the community more, I think would be a great talk at the CC Star PI meeting, because there's a storage area award for CC Star, and this information would be extremely helpful for people proposing for a storage system on their campus, because we went through the experience of selecting a particular technology that later on we ended up changing our minds, and it really ended up taking a lot of time in the whole process. And the kind of information that the person from CSU presented, I think would be excellent to have either at a meeting where the CC Star community gets together, or even maybe have it in the solicitation where there's a pointer to what your GitHub site, because there's some very, very useful information there.
Are you going to the, you're a CC Star, right? Are you going to the CC Star PI meeting next week? You're going? That's an excellent suggestion.
Testing.
I'd suggest that you make that to Kevin when you see him next week.
So great question / comment. And yes, Mike will be at the CC Star next week. So excellent.
So David, can we go to David's, the one that with the numbers? I want to understand a little bit better the 15 days to train. If you can, to what extent can you slice it up? If you had 5 times the number of nodes, would it reduce it to 5?
We think it's scalable. We would love to scale up the number and get this done more quickly. That would be a huge benefit.
And the corollary is: is the way that you run things, is the number of GPUs that you have available to you? Can you deal with variations that it grows and shrinks and grows and shrinks?
At the moment, the way we're configured, we have to have the same configuration throughout the life of the training. We have not figured out we haven't developed an approach to have it go up and down over the course of the training.
I think we reserved a bunch of nodes for you, right?
Yeah, we're running 6 nodes with 8 in each, yeah.
Okay.
So those are reserved just for this group.
Okay, fine. So I now understand how you're doing this. And then there was the comment on high data transfer speed between all nodes.
It is extremely parallel, but there is still some communication between the nodes. The other projects we're on developing similar types of foundation models are using supercomputers with MPI. And so I don't know that if NVLink is there between every single node. Maybe you guys know?
Not for A10s.
Yeah, okay. So, if it was NVLink between the A10s, at least that little piece of it, I don't know that that's a bottleneck. I think the reads right now is where, if anything, that's one of the.
So if you are, so then the 4 terabyte cache distribute across each node. So DMA gives you a node with 8 A10s, and then 6 of them. Why 6?
6 nodes with 8 GPUs each, right?
Oh, now I understand. So now you have inside one of these nodes with 8 A10s, you use all 4 terabyte of cache in order to fill it for all 8 of them?
It distributes. So if there's 4 nodes, it's 1 terabyte each.
Okay.
So it's evenly distributed. There's no replication.
Okay. And where does the higher GPU memory come in? What exactly in your training is affected by that?
So at the moment, what we have to keep doing is reading from the cache and then putting it back, and then swapping, read the next set of tensors from the cache, read the next set of tensors. If we could read once from the cache, it'd be in memory the whole time. And so that 83 million reads would go to, one
basically,
read.
the higher GPU memory is an issue that you would like to benefit from the I/O capability between the GPU and its own memory,
Right.
rather than between the GPU and the system NVMe.
Yes, I guess so, yeah.
Okay,
Yeah.
thank you.
I have a question for you.
Sure.
If you go to the next chart, to be a good community member, we just put the raw data in FS and left it there. We could put it anywhere. So if it's better for us to put that somewhere else, please let us know, because probably we should learn about OSDF, and maybe that's where it goes. I don't know. We'll have to talk about that.
The only advantage that let's destroy some myths about OSDF. First, it's a read-only, so you can't write to it. So basically, when you're writing to it, it's no different than S3. You're just putting. And the benefit where you're getting from the reading is because you have NVMe local. In effect, you have a hierarchy. You have the GRAM in the GPU. You have the NVMe on the host, and then you have the NVMe in a regional cache in OSDF, which is never going to be further away than 500 miles, often actually in the same data center. So if you have stuff that you have to re-access read-wise over and over, because you're changing the NVMe cache all the time, then you actually have a real benefit from OSDF. Otherwise, you don't. Now, the only other advantage of OSDF for you potentially is that it doesn't come out of our disk space. So when we run out of disk space, we have a lot more disk space accessible, just volume, in OSDF than we have in CephFS. CephFS is very limited. I don't remember what it is right now. It's 4 petabyte or something like that at Dima.
I feel bad for leaving the 77 terabytes in there. It doesn't need to be there. I don't know where we should put it.
If this ever becomes a problem, Dima will tell you to clean up and we'll move it elsewhere.
I can count on that.
Basically, we have, if you're thinking about keeping something around just because to keep it around, it is easier for us to support keeping things around like this, your 77 terabyte, inside somewhere in an origin in OSDF, just because. It is no safer there than it is on CephFS. We would generally probably give you a dual copy because we don't trust any one of these origins not to go away. And so it might be a little bit safer in historic, especially last year experience. It's only for volume management that it would be nicer for us to have more of this stuff that nobody uses actively, but it's sort of more like used passively, almost like you're archiving. And if you're really going to archiving and have large volumes, we should have a completely different conversation. Some time ago, a commercial customer of ours at SDSU, not NRP, me with my director's hat on now of SDSU, actually asked us, what's the cheapest archival option that you can suggest? And they asked us, they literally gave us money to give them a list of the different options for archival. And the cheapest archival option that you can do still is tape at either one of the national labs or TAC or NCSA. And both the DOE national labs and TAC and NCSA would love to have you as a customer. So if you wanted a petabyte of backup or 100 terabytes of backup storage just to archive, we can make that deal and figure out what you will have, what your costs would be, and offer this and facilitate those kinds of business arrangements, both for individual PIs as well as for institutions. Like if let's just pick on SDSU. If San Diego State University wanted a petabyte of backup space somewhere else, not in San Diego, we could find you a tape archive that will be happy to take you as a customer at a price that is basically can't be beat. And we've made the comparison with tape archiving, what we do ourselves on disk, and what comes out like Glacier. If I remember correctly, even our disk storage at SDSU, our archival disk storage at SDSU, which is cheaper than Glacier, and it doesn't cost you to access. So Glacier is basically worse possible financially. And if you go to the national labs, there's like a factor of 2 or 3 cheaper still. And so, or if that is of relevant, we should talk.
Just to add to that, so the concrete use case we have is that some of the data we have for certain research, right? I think this is large data. And sometimes some researcher wants access to that data, right? So it's like, let's say passive / archival in between there, right? It's like depending upon an event where somebody wants access to that data, they want to download it, right? And we have ran out of space on our end to host our data, right? Or at least as an individual.
Yeah, and let me explain a little bit why the DOE labs are in this business. The DOE labs that I work with have exabytes to store. And they have exabytes to store that actually get retrieved once a year. And so therefore they have, in an exabyte, your petabyte is like irrelevant. And when you work with them and get a bill, basically make a contract, that contract the price will determined by how much you want to retrieve, because that costs them tape drives, and how much volume that you want to store, that costs them tapes. And the combination price is the price that they give you. So you're basically buying from them retrieval bandwidth and total retrieval volume and tape storage, and the combination has a price. And as long as you're not in the hundreds of petabytes regime, you're irrelevant.
I'll make maybe one more question on this, right? Okay. So one other question, at least I have, is that when you have to move off this large data back to your machines or back to wherever you want to store in archival form, right? It could be your own thing or it could be just the DOE labs, right? The problem is that the bandwidth, let's say you get an email from DIMA, right? Okay, move your data off, right? It can take months to move that data, right? Like depending upon the amount of data you have, right? Are there ways to speed up that movement of data is also another question for us to think.
So again, right now, the standard connectivity inside the SDC data center for storage is within campus. We should easily be at the 100 gigabit capability. And we should actually look through where exactly you're located and that sort of thing. And so 100. Let me think about 100 gigabit is a petabyte a day of retrieval.
No, we just get a gigabit. We don't even get 100 gigabit. Right?
Okay, so we can talk and there's lots of things that we can do there. And in terms of where we're heading as a center, SDSC, through the graces of Scenic, where is he? There we go. Through the graces of Scenic, we're talking about getting our wide area network connectivity upgraded to potentially 800 gig. 800 gig is then 8 petabytes a day. And so for my own research, given that I need to move exabytes around in the world, we're actually working on all kinds of different kinds of mechanisms to, if you're moving an exabyte, you have to upscale your skill set. But for petabyte movement is a non-issue, it's a solved issue.
We don't have petabytes.
Okay.
I have one follow-up question on the 77 terabytes. That data set might be of interest to the broader community. And so what's the process for discussing, here's the data set, would this be worth making available, through
And we're
the national data platform?
I think for the curation part, you talk to NDP, and you'll hear tomorrow from Manish more about this. From the just storing it so that people can access it freely, we can put this 77 terabyte on OSDF, and it's available to anybody who knows how. Okay. So FAIR comes from NDP, just brute force making it available can come from OSCF.
Cool. Okay.
Real quickly, I just want to chime in with kind of a domain-specific user perspective. I've been working on similar problem for astronomy data, but largish data sets. So I would say an OSDF origin NDP is a good path based on what you've said you want to do. Another thing is Amazon's open data is another pathway that you might consider. And I believe our Pan-STARRS multi-petabyte data that's been at Space Telescope is now getting migrated into S3 under that program. So,
Interesting. Thank you.
I'm intrigued by your, this is Willie from Kelsey Fullerton. I'm intrigued by your data collections and the processing model. I know that at Kelsey Fullerton, we do have a newly built GPU nodes. And I know the L4 are lower specifications than the A10s, but we actually put 16 L4s into a GPU node. And I don't know from both data sets and also maybe this will be a good explorations to find out whether the 16 L4 with the higher GPU density model will be able to speed up your processing. But we can offer that for you.
It's interesting. We could look at it because you have the local cache and definitely within a node it's quicker access. Do you know what the memory is on those?
They're 24 gig.
Also, okay, interesting.
I think any other questions? Any other questions, anybody? We're good? Then it's lunchtime. And I want to remind people that there's lunch out there, and then there is in the V room a lunch session. And the lunch session will first have a demo for 20 minutes by Vocarium on what Vocarium is and how it works on the NRP. And then afterwards, there is a Jupyter Light discussion that Rick Wagner will be leading.
And remember to pick up your NRP fan, become a fan of NRP.